Hi everyone. Okay, thanks for checking out this video. So in the last lesson, we talked about how to program the simulation for the simple stochastic model we're talking about with just the transcription and decay of mRNA from one gene. So in this video, we're going to be talking about a more complicated stochastic model where we're going to be doing the stochastic model of the three-gene oscillating network we talked about before. Okay. So I'm just going to come right out and say this. So this is all of this is really scary, and this is probably the scariest thing we've come across so far in this video series. So I'm not even going to try to tell you guys otherwise. Like, this is very intimidating to first look at. So if you're feeling scared of it right now, don't worry, because it is scary to look at. But don't worry, because we're going to go through like part by part, and you guys are going to see that when we look closely at all of this stuff, there's actually nothing new in here. So this lesson is really just going to be like combining stuff we've already talked about in previous lessons. So if you guys have been watching like all the videos up until now so far, like, even though this all looks like a lot, everything in all of this has been already covered, and we're now just kind of like combining everything we've done so far into this this last video. There will be a kind of like summing up of everything. Okay, so let's look at the ODEs first. So if you remember back a couple of videos ago, we talked about the three-gene oscillating network model based on the Goodwin oscillator. So this is just that. So we've already seen this system of ODEs before. But just to give a reminder, so we have gene 1 is activating the transcription of gene 2. So this is the activation Hill function. And remember, it's the activation one because the gene 1 variable is in both the numerator and the denominator. So this kind of saturates to 1 as we get more and more of gene 1. So that's what's activating the transcription of gene 2. And then, so likewise, gene 2 activates the transcription of gene 3. And then gene 3 comes back around to repress the transcription of gene 1. So this is the repression Hill function, which is why we only have the constant in the numerator, and gene 3 is only in the denominator. So again, that's just a review. We've already talked about this a couple of videos ago and done the simulation of it. So this is the ODE model of what we're going to be doing this video. But this video, we're going to be doing the stochastic version of this system. So even though, again, I realize this all looks confusing, but all I did to make this table was for each of these rates, I just put the rate in the rate column and then put what's happening. So let me just give you guys an example. So this this term here, the Hill function, and then k sub 1, all of this term is the production term for gene 1. So I just put all of this whole production term in the rates column, and then for the events, I put gene 1 is going to gene 1 plus 1. Because this is what's happening when a new mRNA of gene 1 is being produced. The level of gene 1 is just going to the current level plus 1. And then so the next rate is gamma sub 1 times G1. So this is the degradation rate for gene 1. So I just took this whole degradation term here and put it in the rate column, and then for the corresponding event, I put gene 1 goes to gene 1 minus 1. So the current level minus 1, because this just means that one mRNA of gene 1 is being broken down. And then I did this for all of for the other two variables, gene 2, just the same thing. Have the production term that's in the rates column, and that corresponds to the event where gene 2 is going up by 1, and then the degradation term corresponds to the event where gene 2 is going down by 1, and then again, same thing for gene 3. So yeah, like I said, like, I know this looks like a lot of math here, but that's all I did. I just took the production terms and put them in the rates column, and those correspond to the variable going up by 1. And then the degradation terms are in the rates column, and those correspond to the variable going down by 1. So this is kind of how we write down mathematically what's going to be happening in the Gillespie simulation. Okay, so now that we've gone through that, let's get started with some of the actual code. So like usual, the first thing I did was just import all the libraries we're going to be using. So we have NumPy, matplotlib, and again, I just need this line because for some reason the new Mac OS matplotlib only works now if I have this line. And then random for choosing the random numbers. Okay, so a lot of this is going to be, if you guys watched the last video with the simpler Gillespie simulation, a lot of this will be basically the same thing, but with more variables and more rates and more, just more of everything, but kind of the same principles. So we'll start off the same way. We'll start off just defining some arrays here. So, like we did last time, this is where we're going to be storing. We're going to be storing the values of all the variables and also storing the time points. So basically, every time an event happens, we're going to update the time point array. We're going to append to it the value of the new time point. So we'll just be appending to it, adding new variables. Adding new values on the end. Because remember, these are dynamic arrays. I think Python actually calls them lists. But the data structure term for these is dynamic arrays because we can add to the end of them new values. And remember, these won't be evenly spaced, so these could be kind of whatever. But yeah, each time an event happens, we append the time point of the new event into this T array here. And then every time an event happens, we also we also append to all of these variable arrays with their updated terms. But so remember something, that whenever an event happens that leads to a change in any of these, we need to append the current value for all of them. So let's say that we have an event with gene 3 increasing by 1. Well, when that happens, we append the +1 value to the gene 3 array. And then we also append for that time point, we append the values for gene 2 and gene 1 not changing. So keep that in mind too, that as these are changing, we need to also, for the ones that aren't changing, we need to append the values for that time point for those two. But yes, that's just a quick example. So, but yeah, just keep in mind, these are dynamic arrays. So every time there's an event, we're just going to be appending the new time point as well as the values of all of the variables at that time point. Okay, so then next we define our end time for the simulation. So we'll just make that 1,000 for now. But I encourage you guys to like play around with different numbers here, different lengths for the simulation to test things out. It's a good way to learn. And then okay, so the next part is we need to define all of our parameters. Sorry, I'm just going to type this out and then I'll explain. Just making sure I got everything. So for each one we have a production parameter, k sub whatever number gene we're talking about, and then we have a degradation parameter, which are the gammas, and then we have c and n for the hill function parameters. And for simplicity, I decided to just keep the c and n the same for all of these. But if you guys want, you could change these up and have different ones for each gene too. But yeah, so actually, just for simplicity, also, I'm just going to be keeping all the k's and gammas also the same here. But yeah, I mean, I encourage you guys to like play around, try making these different, try changing them around and stuff, and see what you get. But for now, I'm just going to make all the production terms 2 and all the degradation terms 0.1. Just keeping it simple. But yeah, I think it's a good idea to like change these around and kind of experiment around with them. And then, so like with before, the actual simulation is going to be happening in a while loop. So the while loop is going to be running while the last value of the t array is less than t end. So this is just saying while the last time point we've recorded, if the last time point so far is less than t end, then we keep doing this loop. So and remember, just the syntax here, t index -1. This is getting the last value in the t array. Okay. So then within the loop, we're going to say we're going to find our current levels of everything first. So this is the same syntax as up here. This is just pulling out the last recorded value in these arrays. So this will start at 0, but once we fill these up with numbers, this will be pulling out the last number in there for each one. So these are our current values of all the variables. And then so next we're going to be defining the rates array. And so I'm actually going to be a little bit lazy with some of this stuff because I don't think you guys want to just watch me typing out like a really long thing. So I'm going to actually just copy and paste some of this stuff in from my previous code. But then I'll explain it. So yeah, so sorry if this is kind of lazy, but I just decided to just copy and paste a little bit of stuff so you guys aren't watching me type for like 5 minutes or something. But so these are all the rates that were in the rates column here. We're just putting these into an array to have them organized and keep track of them. So for each rate, I really just typed it in. So we have some of our parameters here and also the current levels of the genes. So this is our first one here with the repression hill function times k sub 1. That's this rate here. And then gamma sub 1 times the current level of gene 1. That's right here. And then I also just did that just for all of the rest of these rates. I just typed them right into this rates array here. So sorry if I'm kind of being lazy by copy and pasting, but I just didn't think you guys want to watch me type for like a couple minutes or whatever. And then so next we're going to say rate sum, exactly what it sounds like, the sum of the rates. And remember, so these are actually, some of these are changing. This is just important to note, some of these are changing at different time points. So some of these depend on, so like k sub 1 and all the k's and all the gammas and c and n are fixed and not changing, but the current levels of the genes are changing from time point to time point. So these rates, like these numbers actually can be changing. They're dynamic themselves. So these current levels of the genes that are going into the rates, like these current levels are changing. So that's why it's important to like have this be calculated every time point because these can be changing. So just important to note. And then the rate sum. Okay, so the next part is so like we've been talking about, the first thing we need to choose is the time point of the next event that's going to happen. So if we're at some time t, we need to pick a value tau so that we can define t plus tau to be the time point when the next event will occur. So the way we do that is by taking a draw from a exponential distribution. We're taking a random draw from a exponential distribution. So we're going to do that using the numpy.random.exponential function. And then we're going to define our scale here to be 1 over rate sum. So this is a little bit of confusing syntax here because usually when we talk about an exponential distribution, we have some parameter lambda so that it's like the PDF for the exponential distribution is lambda e to the negative lambda x, which is possibly good for you guys to memorize if you have time. But yeah, usually we give some parameter lambda, but here, what the scale parameter here is 1 over lambda. So if we want our lambda to be the sum of the rates, we need to actually pass in 1 over lambda for the scale. And another way to think of this is that for the exponential distribution, when we have this parameter lambda in the PDF, the mean of the distribution is 1 over lambda. So we can think of the scale parameter here in the numpy function. This scale is whatever we want the mean to be. not the parameter lambda. It's 1 over lambda, but the scale is like the mean of the distribution, not the lambda parameter. It's 1 over the lambda parameter. So that's just something to kind of try to remember and keep in mind, because it's a little bit of confusing syntax, because usually you would pass the parameter lambda, but we're passing 1 over lambda here. Okay, but then when we have tau, so our next time point is going to be the current time point plus tau. That's how we're choosing our next time point. So we're going to say t.append. So remember, this syntax here is the last time point we have recorded. So this is our current time point. T index -1, just our current time point, plus tau. So this is recording the next time point as being the current time point plus this tau that we just randomly picked. Okay, so then after we choose the time point of the next event, we need to choose which event will actually be happening. So like we said before, the way we do this is by taking a random draw of these events, but each event is properly weighted based on what its rate is. So the way we do this is by using the sum of all the rates and then the probability for each one, like the probability of this event G1 going to G1 plus 1. The probability of this event happening will be this rate over the sum of all the rates. Okay, so that's how we're weighting the probabilities. And then the probability of gene 1 going to gene 1 minus 1 will be this rate gamma sub 1 times gene 1 over the sum of all the rates. So that's how we're weighting the probabilities properly to account for the weights. Okay, so the first thing we're going to do is just pick a random number from a uniform distribution between 0 and 1. Okay, so we're just going to call that rand. So this is just some random decimal between 0 and 1. And then, again, I'm going to be a little bit lazy with this part. Sorry about that. I know this is kind of lazy, but I don't think you guys want to see me typing for like 5 minutes trying to type all this stuff out. So I'm actually just going to copy and paste it and then explain it to you guys. So sorry for being kind of lazy with this. But so this is the actual code for doing this weighted, the weighted probabilities and just a random draw from these weighted probabilities. So this is how we're actually going to implement that. So what we're going to do here is multiply our random decimal between 0 and 1. This will be multiplied by the sum of all the rates. And then we're going to check where this product falls. So we're going to say if this product is less than the first number in the rates array, then that will be, because remember, the first element in the rates array is this right here. So we're going to say if, so basically how we're going to do this is we're going to say if this random product, the random number times the rate sum, if this falls between 0 and this number, then it's going to be this event. And then we're going to say we're going to just go down the line and say, okay, if that doesn't happen, we're going to say if the random product falls between this event and the sum of these two events, then this event will be which one happens. So we're kind of like summing up the rates as we go down, and then whatever sums our random number falls between, that's how we're going to choose what event happens. So you guys may need to like wrap your head around this a little bit, because I know that when I first saw this, I had to wrap my head around it a little bit, but that's how we're doing it. So that's what all this code is just checking where this random product falls. If it falls between 0 and this rate, we choose this event. If it falls between this rate and the sum of these two rates, we choose this event. If it falls between the sum of these two rates and the sum of these three rates, then we choose this event. If it falls between the sum of these three rates and the sum of these four rates, we choose this event. And then so on and so on. We're just summing up. We're checking what sum of rates it falls between, and that's how we choose which event to do. And then so what do we do once we actually choose the event? Once we choose which event's happening, we need to update all of the variable arrays accordingly. So if we choose, let's say we choose the first event. Let's say that our random product falls between 0 and this rate. So okay, so then we know that the event happening is that gene 1 is going to gene 1 plus 1, meaning that a new RNA of gene 1 is being produced. So the way we update this is we append the gene 1 array. Sorry, it's this one here. Yeah, sorry. We append the gene 1 array to be its current level plus 1. So we're adding a new number to the gene 1 array that's the current level of gene 1 plus 1. And then for gene 2 and gene 3, we append these arrays with just their current level without changing it. So if all these were starting at 0 and we choose this event to happen, then we're going to append a 1 to the gene 1 array, and we're going to append zeros to the gene 2 and gene 3 arrays. Because remember, we still need to, like, each array still has to have a value at every time point. So even if nothing is actually changing with gene 2 and gene 3, we still need to append to these arrays just so that they'll have values at this time point. But if nothing's changing, we just append whatever their last value was. I guess we actually could have, instead of just doing the syntax, we could have just used the current gene 1 and all these variables, could have just put those here, which I kind of forgot about, so sorry about that. But it'll be fine this way too. But yeah, so, and then just another, I mean, you guys might get it already, but just give another example. Let's say we choose this event to happen. So let's say that the random product is between this number and the sum of these two numbers. So if we choose this event to happen, which is a breakdown of a gene 1 RNA, if this is what's happening, then we just append the gene 1 array with 1 less than the current value. And then gene 2 and gene 3, we just append with the current value. And then same thing just down the line. So this is the gene 2 production event. So in this case, choosing this event here, we're going to append the gene 2 array with 1 plus the current value. And then for gene 1 and gene 3, we just append with the current value. And then, yeah, so it's just for each if statement, that's just all we're doing is just whatever's being changed, we append a new value accordingly. It'll either be plus 1 or minus 1. And then with the ones that aren't being changed, we still need to append a value so that they'll have some value at this time point. But if nothing's being changed, then we just append the current value using the syntax here, the minus 1 index syntax. Okay, so I know this part here, the weighted probability random draw, this is a little bit to like wrap your head around and a little bit confusing. Because I was also pretty confused when I first saw it for the first time. But yeah, if you think about it a little bit, I think it all kind of makes sense. Yeah, so I mean, okay, so that's basically it for so this whole thing, this loop will just run until the last time point is either greater than or equal t end, and then it'll stop, and then we'll have all of these arrays get filled up with all of their time points for t, and then the values of genes 1, 2, and 3. Okay, so yeah, that's basically it. So now we're just going to plot the results. So again, sorry for more laziness, but I'm just going to copy and paste this block of code in here. So what this is doing here is the matplotlib code. I actually don't think, I mean, for this stuff, I just copy and pasted out of just like laziness and not wanting to have you guys watch me type the whole thing for 5 minutes. But for the matplotlib code, I actually think it like doesn't really make sense to memorize all the syntax. So I usually just copy and paste the matplotlib stuff from like a previous code just to save time. But yeah, so what this is doing here is just we're going to make a plot with 3 subplots. So we call the subplots x1, x2, and x3. So for x1, we're going to be plotting the time points and the values of gene 1, and we'll label it gene 1 and color it blue. X2, we're plotting gene 2, coloring it red and labeling gene 2. And then x3, same thing, gene 3, coloring it green and labeling it. And then we're gonna only label the axes on x1 just because I don't want to be redundant. But yeah, we'll label the y-axis number for the number of RNAs for the gene, and then the x-axis will be the time axis. And then this line here is just setting the legend, so giving the labels. And then yeah, plt.show is just displaying the plot. Okay, so let me just look things over and make sure I got everything. Yeah, so hopefully this works. So, okay. Okay, so it looks like it worked okay. So as you can see, so each one is kind of having the oscillations that we talked about, but you can also see that they're sort of like unevenly spaced because of the stochastic nature of this model. Compared to like, remember, if you guys remember with like the deterministic ODE model, when we did the oscillator, they were like, of course, very smooth. But this is stochastic, so they're still oscillating, but it's much more random, which is to be expected. And of course, if you guys run this like multiple times, you're going to get different results each time. But especially with Gene 3, we can sort of see the oscillations kind of emerging. But yeah, so I mean, I guess that's it for this simulation. But like usual, I encourage you guys to like play around with different parameter sets, different end times and stuff like that. Maybe try like changing these up. Maybe have the different genes have different production and degradation terms. Yeah, just kind of hinge around things, see what happens. That's a good way to learn, I think. And yeah, so thanks for watching this video, and also thanks for watching this video series if you've been watching all of them. So just to kind of like conclude, so we started out with like a very simple ODE model of just the central dogma, and we sort of like built on it little by little. And now the last thing is that we now have this stochastic model of a gene network. And you guys can, of course, like add more genes to this, make it as complex as you want. You can have like 100 genes or something. Well, yeah, so I think that's all for this video, and I think this is also going to be the last video in the introductory video series I'm doing. But I would like to continue making these videos, these tutorials of like different topics. So if there's any topics you guys want to hear about in computational biology, just leave a comment, and if I like know how to do it, I'll definitely try to make a tutorial for you guys to explain it. But yeah, I mean, thanks for watching. I hope you guys enjoyed this video series. I definitely enjoyed making it, and hope that you guys learned something. Thanks, and see you next time.